Hello, it's another video. Well, we're continuing about calculus for AP Physics, and we talked all about derivatives the first time. For 45 minutes, we talked about derivatives, where you find the slope of some function. And the slope's a simple idea. The slope at a point is, well, you have to kind of sneak up on it with a limiting process to make any sense of that. And then there's a series of tips and tricks for how you actually go about doing that with a given function. Well, today we're going to do kind of the opposite. This is called integral calculus, and I think I'll start with the same sort of example I had before with that hill on rugby that I used to get the cross-country and track teams on to run up to hill work. The hill looks something like that. That's exaggerated in steepness. It's not really that steep, but we already did this limiting process of finding the slope at some arbitrary point like here by, well, maybe we did it back here, and we did it by saying we had the rise over the run, and this was, f of x plus delta x, and this was x plus delta x, and this was x, and we took the limit of the slope as delta x approached 0. That's nice. We got slope data, if that's what we wanted to know. If what we wanted to know was how steep is this hill at some point, we'd have to go through this process of taking the derivative of the thing. But what if we flip things around? What if we knew the slope at every point? And you could do that with something like an inclinometer. You could have a little, just imagine this has got a protractor on it and it's hanging down, and you tilt it and you can see where the little, penny hanging from a string goes to. Or maybe it's just marked in slopes, or maybe you just, you have a slopometer, a slopometer, and you get slope data. And what you want to know is not how steep it is. You know how steep it is at every point because you walk all the way up the hill with your little slope meter. What you want to know is how tall the hill is. So how do you find the height of the hill if you know how steep it is? Pretty easy. Remember, if slope is rise over run, and you want to know the rise is the slope, I keep running out of room, times the run. So you would just multiply. Really what you do is, if the slope is called f of x, like the slope has a name, it is f of x. F of x no longer represents the height of the hill. It represents the slope of the hill. I just changed what f means here. So in any case, what we want to say is that the height of something, I don't want to say this, the height is going to be the slope times the run. So I'm inclined to say f of x times delta x, but remember the problem. The problem is it keeps changing on us. The slope is not the same everywhere. If it were one straight line like that, then it'd be really easy. You would have one slope, you multiply by the run, you get the rise. But it's got lots of different slopes. You got to multiply by these little runs to get rises, and you have to add them up. So what I'm going to do is have you conceive of the hill as having lots of little parts. And by the way, I don't remember if I even said this just a minute ago. Do you realize, really, if you have, say, the slope here, and this is the run, and you have a nice even slope, a nice steady slope, that really slope times run is an area. If you multiply how steep a hill is, it's one number times how wide it is, you get the height, but it shows up, it's represented as an area. It's simply the product of these two things. That's how you find the area of a box. The problem is, we don't just want the area of a box, we want the area of some crazy thing. Now, by the way, I don't like what I did just a minute ago. I don't like what I did. I'm not going to completely retract it. I can't un-erase it and re-erase it. But I drew the hill like this. Actually, I would like to go back to thinking about the original hill. I mean, you can have a hill with slopes like this, but I really meant this to be a picture of the hill itself. Its slope, let's think about it. Its slope starts out not very steep, maybe even zero, might not be zero. Then it gets steeper, see? It reaches maximum steepness in here somewhere, and then the steepness kind of comes back down. I don't know if it comes back down to zero or not. Maybe it doesn't. Maybe it doesn't come back down to zero. But this is a better graph, really, of that hill on Rugby than the thing I drew a minute ago. Or a better graph of the slope of the hill. So how do we find this area so we can get this height? Well, that's a funny shape there. There's some neat ways to find areas of funny shapes. One of them is really elegant and kind of old-timey, old school sort of a thing. You literally could graph it on graph paper and take some scissors and cut out the shape. And on a really accurate scale, you could weigh it. And then you could weigh a known area of graph paper and literally get it from the weight. That's not all that bad of an idea. It works if you got a sensitive enough scale. But that's not what we're going to do here, because we're going to learn something. What I'm going to do is imagine breaking it into little parts. If it were on graph paper, you could do counting the squares. And there's a little rule. I've done this lots of times. I've counted squares to integrate. What you can do is you can decide you're going to count a square as one whole square if more than half of it is under the curve. And if less than half, you don't count it. And then you get a whole number of little squares, and it's an approximation. Well, let's talk about how you could do that here. What I could do is I could start by saying, all right, the height of the hill at this point is whatever, and I could make a box that has this height. I hope you can see this okay. I hope you can. You could call this height f of x, and you could call this width delta x, and this is the area of a box. It's clearly too small. I mean, for one thing, I'm going to have a lot of boxes, but it's too small to get this whole thing. In fact, there should have been a box back here. Oh, dang it. My tape's coming loose. I'm doing this with my cell phone. It's pathetic. Maybe it'll stick this time. I hope so. Come on, stick. Stick! Maybe it'll make it through the video. In any case, so there's that area, but there's another one. And another one. And another one. That's better. And here's another one. Ooh, that one's too big. This one's too big. I kind of like in this particular example how some of them are too big and some of them are too small, and maybe it makes up for it. But I could add them all up. And how do you write that you're adding a bunch of things up? What you do is you say, I want to know that the area of the whole thing is going to be the sum of a bunch of f of x's. They're not all the same f of x, they're different f of x's. But I want to multiply them times a little delta x's and add them all up. I guess I could say from n equals 0 to whatever, how many I've got. But you know it's not going to be completely right. It's going to be off a little bit. How can I make it better? Well, clearly I can make it better by using skinnier little boxes. If I use skinnier boxes, I get a better approximation. How skinny? Infinitely skinny. Infinitesimally wide boxes. In other words, what I'm going to do is take the, I should write it this way, I'm going to find the limit as delta x goes to 0 of this sum. It's very hard to actually do it because there's an infinite number of them. That's where the calculus tricks come in. We have a way of writing this. I hope this thing stays up. It's on there pretty good now, I think. Yeah. So what I call this, the symbol, and I'm going to admit something. I took many calculus courses before I realized the origin of the symbol. I forget when I finally learned it. It looks like that, and I just thought it's the integration symbol. It's an integral symbol. Well, guess what it is? It is an S. This is also an S. This is the capital version of the uppercase Greek sigma, sum, sum. This is a big lazy S. And so I'm going to write f of x here. But you know what we did with the slopes? We went from calling the finite decent sized chunks, which are called delta x. We squishified them all the way down to nothing. We started calling them dx, like a dx is an infinitesimal, itty bitty delta x. Same thing here. They get real small like that. So what we call this, the wording we use, is this is the integral of f of x with respect to x. And it is an area. It is an infinite number of infinitesimally small things added up to get some finite amount. I would actually like to use this to get some. I'm not going to do the hill on rugby. I didn't come up with a function for that. I think I'd rather do a function that we already have. I know what I'll do. I got one. I'm going to do one that's not the simplest possible one, but not too bad either. Let's just do the parabola. Let's just do y equals x squared. Let's say that f of x is x squared. And that looks like this. I'm going to draw it reasonably well. Let's see. It goes like that. And this is, it's 2, let's say. And it goes up to 4 when you get out to 2. And when it's 1, it's 1. That's not bad. That's good enough. What if I wanted to know this area? Now, I don't know if this is a hill and we're trying to find out how tall it is or if it's some abstract thing, but I want to find that area. So let's see here. I could approximate it in various ways. Here's one approximation you might try. It's a lousy one, but you could try it. You could say, you know what, it's, I don't know, look at the triangle. See the triangle? The triangle has a width of 2 and a height of 4, and half the base times the height is 4. So I could estimate it at 4, but no, that's not right. It's less than 4, isn't it? Of course it's less than 4. No, it's less than 4. How much less than 4? I could do better. I could probably do a little triangle here and another triangle here. That'd be, a trapezoid. That's what that is. Oh yeah. What I could do is I could say there's a box here that's 1 times 1 is 1. There's a triangle here that's 3 tall and 1 wide and half, because it's a triangle, makes 1.5. Okay, maybe. And this one here is like a half. And so then I get a half and 1.5, 1 is like 3. Maybe it's 3. But actually, it's a little bit less than 3. That doesn't look quite right. It's probably 2 point something. Gosh, I don't know what it is. What am I going to do? Well, what I'm going to do is integrate this thing. I'm going to take the integral of x squared with respect to x. I'm going to multiply all these little x squareds times the little dx's and add them all up. But nobody's taught me how to do that yet. Well, I'm going to inspire us to do something by the following argument. And again, I'm not your calculus teacher. I'm just trying to hand waving. See, I do waving hands. I'm trying to do a little hand waving lead into this and have it sort of make sense to you intuitively, even if you need to learn it a whole lot better in calculus class. So here's the deal. Notice that taking a derivative is finding a slope. And taking a slope is it's kind of like dividing, because you divide the rise by the run. Notice that an area, it's like multiplying, because you're multiplying this times this. To get the area of a rectangle, you multiply the base times the height. Multiplying is the opposite of dividing. In fact, when you multiply two numbers, like say 3 times 4, you get 12, but you can take 12 divided by 4 and get 3. In other words, you work in opposite directions. They're inverse operations, you could say. like addition and subtraction are inverse things. Multiplication and division are inverse things. And integration and differentiation, we're taking derivatives, derivatizing, are inverse operations. They're opposites. So if they're opposites, it's like that game, that TV game show, you know. I think Alex Trebek is still around. He's suffering. He's sick. But anyway, it's called Jeopardy. In Jeopardy, you could go like, you know, derivatives for 200. And it's like, ding, 2x. You know, what is, and then you say, what is the derivative of x squared? You see how the Jeopardy contestant worked backwards and told you? I mean, you knew that the derivative of x squared, you know, if you do, if that's f of x, then f prime of x is 2x. You learned that. You learned it in the last video. But you could work backwards and say, like, whose derivative am I? You simply work backwards. And so the question is, it's a little bit harder. It's a little bit trickier than taking the derivative. How do you work backwards to find whose derivative, like whose derivative, see, I'll write it out, whose derivative is x squared? You know, if you were taking the derivative, you knock the power down. So I'm thinking x cubed, maybe. Maybe it's x cubed. Maybe it's x cubed. Is it x cubed? One problem. If you take the derivative of x cubed, you're going to get 3x squared. Oops, I want just plain x squared, not 3x squared. I want just x squared. Oh, I need to have a 1/3 sitting out in front of my x cubed. So when this 3 comes walking out the front door, the 1/3 jumps it, neutralizes it by making it into a 1. This does the trick, doesn't it? See, it's a little bit trickier. If I want to say, you know, like the integral of x to the n dx, and what is it? I guess it's, look, 1 over n plus 1. See, I should have made you think about that. I would if it was class. Like that, right? If I plug in the 2, you know, for like a 2 for n, then I get that the integral of x squared with respect to x is 1 over 2 plus 1, 1/3 x cubed. It works. You just go backwards. And so the answer to my question is x cubed. Guess what the integral of cosine x is? Sine x. What do you think the integral of sine of 2x is? It's probably -1/2 cosine 2x, I think. It's whatever works when you go backwards with it. It's a little harder, and the tricks are harder. For instance, there's a trick that's like the product rule, but like if you have like the integral of two functions multiplied together, but it's a good bit harder than the product rule. It's called integration by parts. It's like integral of u dv equals uv minus integral of v du. See, it's stuff you learn when you take a calculus course, but we'll do the easy examples. So I want to go back to this. I just found out the integral is 1/3 x cubed, so what do I do with that? Well, 1/3 x cubed is actually the function that tells you the slope itself at any point. It doesn't quite give you the answer for the area. It's not going to quite spit out a number just yet, because all we found so far is called an indefinite integral. An indefinite integral, indefinite integral is just a function. It's just the function that tells you what shape the graph's going to be when you find the area. But what we want is an actual value. So we want to find a definite integral, and that is an actual area, an actual value, like a number. I want a number, because I think it's a little less than 3 in my example, and I want a number. I'll tell you what you do. Here's what you do. You do this. Okay, you read that? Okay. So what you do is you write it like this. You say this area that you're looking for, the definite integral, is the integral of, say, x squared dx, but you put what's called limits on it. It's where you start and where you end. I want to know the area from here to here. I want to know from x equals 0 all the way out to x equals 2, or wherever it is I feel like stopping. And that's where I feel like stopping. So what you do, you figure it out and you get x, well, it's x cubed over 3. I could put it as a 1/3 or over 3, same thing. And then you draw a bar like that, and on there you put 0 to 2. And what you do, just telling you what you do, is you plug in the top number and you evaluate that. So you're going to do this, come down here. You're going to put 2 cubed over 3. And you subtract from that what you get when you put in the bottom number. So I put in 0. Well, that's easy. 0 cubed over 3. And that gives you 8/3. And 8/3 happens to be 2.67. I'm feeling good. Remember I said it was a little less than 3? It is. It's 2.66666, like that. So I just found it's 8/3 is the area. What if I didn't need the area of the whole thing? What if I was only interested in this area here? What if I only wanted to know this part? Well, it's clearly less. It's less by a little less than a half. So it's probably, well, it's 2 point something. What do? You would only integrate from 1 to 2, right? And then you put a 1 down here. And then you put a 1 right here. And it'd be 8/3 minus 1/3 is 7/3, and that'd be 2.33. And I figured it was a little less than 2.5. That sounds right to me. Okay, so we've just learned how to do an indefinite integral. I'm sorry, an indefinite integral is a function. And we've learned how to get a specific numerical value out of it by finding an area starting here, ending here, and there you go. And it's called a definite integral. Now there's something, those of you who already took calculus might have been saying, but wait, he didn't what? I forgot something. No, I didn't really forget it. I was thinking it the whole time. It's the thing you lose obnoxious points on calculus tests for. Like, you got everything right. You nailed this test. You're going to have 100 on it. And the teacher's knocking off a couple points here and there because you forgot this stupid thing called plus C, where you're supposed to write the constant of integration. In other words, it's like this. This thing I said, you know, when I did the indefinite integral, the integral of x squared dx, and I said that, my math teacher would come along and say, plus C, and count off 5 points or something right there on my test, because I didn't say this obligatory, ritualistic plus C. But there's a reason for it. There really is. Here's the reason for it. With that hill, where we're trying to find the height of the hill on rugby, and I do it with my little slopeometer, and you know, maybe I have the, you know, funny function that goes like this, and I integrated it and found the area, and I started here, and maybe I even did a definite integral. I could get the height of the hill above its base, but the bottom of the hill over here on rugby, and I'm actually kind of pointing at it right now, it's about 400 or 500 meters in that direction. It's already about 300 meters above sea level. Oh, so did I want the height of the hill above a given place? Or did I want how high the hill is above the ocean, where you really start from? And the thing is, lots of different hills in different places all around the country could have the same slope graph and yet go to very different elevations at the top because of where they start at the bottom. So really, it's like this. There are a lot of functions that have x squared as their derivative. Who all has x squared as their derivative? Well, we already found out that x cubed over 3 has x squared as its derivative. Sure it does, but I'll tell you another one. X squared over 3 plus 4 also has, x cubed over 3 plus 4 also has x squared as its derivative. Because what's the derivative of 4? Nothing. Do I know it's 4? No, it could be 17. I don't know what it is. It could be anything from what I've been told so far, plus C. Practically speaking, if I'm finding the height of the elevation above sea level of the hill on rugby, The c would be the bottom of the hill. It's the constant 300. But I would need more information to know that. So generally when you do an indefinite integral, you just put this plus c thing because you don't know. If you're provided with more information, some initial conditions on that thing, like the bottom, then you know what c is. But that's something that might not be given to the problem. A lot of times on math tests, they don't give any context for this. So you just say plus c, or you lose 5 points. So in any case, we just learned how to do integration, I guess. And what else should I say about it? You know, kinematics makes use of this. I'm going to do something right quick. You see, I could start with the idea that there's a uniform acceleration, and the acceleration is a. I know that's a very redundant statement. The a is a, but my point is, I want this to be a constant value. I'm just saying the acceleration is a. Now you might know, I hope you, maybe you know, that if you had an a versus t graph and you found an area under it, just look at the units. The units will do the trick for you. If this is meters per second, and this is seconds, and you multiply them, so one of the seconds cancels out, you get some meters per second. You get delta V. The area of this thing is delta V. So generally speaking, if I want V is the integral of A with respect to T. The DTs, see, we were saying like dx in our examples because, you know, math classes it's y and an x. Tell you what, in physics, time is of the essence. So it's time usually we're talking about. And so we're integrating with respect to time. And this gives you a speed. But what do you get when you do this? Well, a is a constant. What is the integral of a constant? It's a times t. So I could just say, oh, there, v equals at. Well, maybe. But you know, it's really plus a constant because you might have already been moving. And here the context is so simple. If you're already moving, it's called v initial. I'm going to write it as v naught. Sometimes I write v sub I, but I can write naught, you know, like British sounding. So it's like plus v naught. Well, nice. Oh yeah, I knew that. How fast I end up going is how fast I was going in the first place, plus how much I sped up. What about if I want to know where I am? Now here, it's like if you had a graph of speed versus time, you had some area to find, that would be your delta x. So this could be how far I went. Oh, I guess I'm supposed to integrate v dt, but I already know that v is a couple of terms thrown together. It's at plus v naught. And when I integrate that, do you know what the integral of at is? Because there's a little 1 on that. If there's a 1 there, that means before you derivatized it, there must have been a 2 there. But you need a half standing outside out the front door to jump the 2 when it comes out the door and make it into a 1. So really this becomes 1/2 at squared plus, well, actually the integral of v naught is v naught times t to the 0. Add 1 to the 0 and you get a 1. And so it's going to be v naught t. Now, is that true? Is that where you end up? Well, what about the plus c? It's plus a constant, right? But the context of this is obvious, I believe. The constant is where you started, x naught. Now, the way I just did this, I started with the highest order term. This is a way you can write it, but it usually gets written the other way around. And I usually write it the other way around. And I've had little philosophical discussions with a colleague on which one makes more sense. When you approach this thing through calculus and make it look like you do it in a calculus class, it's natural to come out with the higher order term, the higher powered term first in descending order like that. It's kind of because you say plus c, like in calculus class. Not only that, when you write a quadratic, you generally have, you list the square first, then the first power, then the constant one. But this makes more physical sense to me because when I ask, where are you? Oh, where'd you end up? And it's like, I don't know. And you go, well, okay, well, where'd you start out? Oh, I started at X naught. Yeah, but you were moving. You didn't stay there. Yeah. How fast are you going? Oh, no, it kept changing. Okay, well, how fast did you start out moving? Oh, V naught. Okay, so V naught T. But you didn't stay the same speed. Oh, yeah, accelerated. And then this half AT squared is this cute little correction, an additional term to refine your answer and nail down just where you are. Now notice all of this assume uniform acceleration. Don't have to assume uniform acceleration. I'm going to shut up about this in just a minute because I'm not going to like try to make you do a lot of integral calculus right now. We'll have reason to do more of it later in other contexts because there's other things we want to find areas of besides just V versus T graphs or A versus T graphs. Kinematics is one application of this. There's plenty more that we'll see later. But you might think about what if you had a uniform rate of change of acceleration. You could call it like B, and it's the B could be the time rate of change, that it could be like dA dt, and you could have a B in here. You might think about how that would look. I'm not going to do that one for you right now. I might do it in class. It'd be sort of an extension beyond the old uniform acceleration thing you've learned before. So we just learned what integral calculus is. It's the opposite of taking a derivative. You could call it underivatizing, but then there's little things like the constant of integration, the difference between a definite and an indefinite integral, and it's generally harder, and that's why they do differential calculus first, usually. We will talk more in class about all this stuff, and we'll see you later.